Chapter 4, Section 7 in the 8th grade textbook is entitled Real Numbers. What we're talking about here are types of numbers. There's lots of different types of numbers you're already familiar with. For instance, when we talk about integers, we talk about numbers that are on the number line. We talk about the whole numbers, or the counting numbers, or the natural numbers, whatever you want to call it. That's our positive numbers from 1 on up. This is all fitting into that category of the concept of real numbers. Most numbers are types of real numbers. There's a couple specific types that they're going to talk about here. Most specifically, they're going to talk about the concept of an irrational number. An irrational number is a number that cannot be expressed as a ratio of two integers or as a repeating or terminating decimal. That's a number that cannot be expressed as a ratio of two integers or as a repeating or terminating decimal. So what they're saying there, in essence, in the simplest way possible, is it's something that cannot be written as a fraction. Remember, if we can write it as a fraction, which is something we've already talked about many times over the course of the last couple of years, that's called a rational number. And there's seemingly in our minds, by comparison, it seems like there would be a lot more of those because we think about all the numbers we write in class and how many of them we can write as fractions. Of course, numbers are infinite, so there's an infinite number of both. But seemingly to us, there would be a whole lot more rational numbers than irrational numbers based on how many times we write things as fractions in this class. Real number? Real number is a rational or irrational number. And the density property? The density property is the property that states that between any two real numbers, there is always another real number. So what we want to do is go ahead and look at the correlations between all the different types of numbers, and that's actually not in your note-taking guide. You can find that correlation illustration, though, on page 195 in your textbook, so I'm going to go ahead and bring that up right now here. Page 195 shows the relationships between all the different types of numbers, all the different types of numbers that are real numbers here. And there is that illustration that you can find on page 195 in your textbook. As you can see, this illustration shows that everything we're talking about here are real numbers. Most things will fit into this category of real numbers. The things that aren't real numbers are called imaginary numbers, and the best example I can give of that, although it won't be well understood right now, would be the square root of a negative number. Right now we know that we can't do the square root of a negative number because there's no number I can multiply by itself to make a negative, ergo I can't then take the square root of a negative. All right, those are imaginary numbers. Those would not fit into this category. But pretty much everything else is going to fit somewhere into this category of real numbers. So we start off, as we said, with the natural numbers. Those are your counting numbers, so that's your 1, your 2, your 3, your 4, your 5, your 6, your 7, and on up. The whole numbers is that same list, but it adds the concept of 0. Then we've got the integers, and as you can see, we're starting to include more numbers. That's why the bubble is getting bigger here. When we're talking about integers, those are anything that appear on the number line. So that's your counting numbers, their opposites then, and 0. Then we get out here to the idea of rational numbers. Rational numbers, again, are anything we can write as a fraction. So as you can see, for instance, they've got 27 over 4 there, which doesn't fit into any of those other categories, but would be rational because it is itself a fraction. 4.5 is an example. 4.5 can be written as a fraction, 9 over 2. And of course, we could multiply that up, and it would still be anything equivalent to that 4.5. Here we have 0.3 repeating. Repeating numbers are rational because they can be expressed as a fraction. That is not true for any old number that just goes on and on and on, but it is true for any number that repeats with a pattern. For instance, like the 0.3 repeating here, which is of course 1/3 as a fraction. Here, the next one there, they've got negative 6 over 7, itself being a fraction. Of course, that would fit into the definition there. And then the square root of 4, square root of 4 being equal to 2, of course. 2 is something we can write as a fraction, 2 over 1, so that's going to make it rational. But that's all old news. What they're really spending time talking about here is the idea of irrational numbers. As you recall me saying back over here when we were talking about rational numbers, when we have repetition in a decimal form, If there's a pattern to it, that's going to make it fit into the idea of being a rational number. If it's a decimal that just goes on and on and on, but does not have a pattern to it, that's going to be an irrational number. And that's what you see represented here. Square root of 17 and the opposite of the square root of 11 and the square root of 2, you can punch those in on your calculator, and you can see those are numbers that will take up the entire screen. That is not a finite end either. They will keep going without a pattern. That's going to make them be irrational. Pi is another example of an irrational number. I know sometimes we approximate that as 22/7, but that's all it is. It's an approximation. In reality, it can't be written as a fraction because it goes on and on forever, again, without a pattern. The without a pattern part is of the utmost importance. It can go on and on, but if it has a pattern, it's rational. If it does not have a pattern, it's an irrational number. And again, you can go ahead and take a look at this chart, which is on page 195 in your textbook. All right, so let's go ahead and return to the presentation now. And we'll go ahead and take a look at the first example here, where they're asking us to write all the names that apply to each number. And the first question they've given us here is the square root of 5. Well, if we take a look at this, the first thing they're talking about is 5 by itself would be a natural number, but it's not a perfect square here. So we got to figure out where this is going to fit into that illustration. So if we flip back to the 195 presentation here, we can go ahead and punch the square root of 5 in on a calculator to see what pops up there. And when we punch in the square root of 5, what we see is the result happens to be 2.236067978. So what we see is that number is going on and on and on and on here, but it does not have a pattern to it. And because it's going on and on and on forever here without a pattern, that's going to fit into this category of irrational numbers. Well, once it's an irrational number, as you can see, that's not linked with any of these over here. So the only answer we're going to be able to give here, as far as the 5 goes, is in that chart, is going to be an irrational number. You can see whole is listed there. That's actually a mistaken answer there. It's just an irrational number. All these numbers that we saw on that chart there, including the irrational numbers, again, all fall under this subcategory of real numbers. Again, the only thing that's really not going to fit into that mix that will probably be anything you'll study anytime in your secondary career would be the square roots of negative numbers. So all of them are pretty much going to fit into the concept of real. So as we toggle back to the notes here, we also see that real is listed here. Negative 12.75. So if we toggle back to the chart here, it would not fit into the concept of integers, whole numbers, or natural numbers. It's not an integer because it wouldn't be on a number line, so it can't be any of these either. But it is something that would be rational because it can be written as a fraction. Now, most of us are probably sitting there and thinking 12 3/4 right now because that is how I would write that as a mixed number. Obviously, that's not exactly what they would be wanting, but of course we can change that mixed number into an improper fraction pretty easily. 12 times 4 is 48 plus 3 is 51. 51 over 4 is going to make that happen. So it will fit into the concept of being a rational number, something we can write as a fraction. And again, anything that fits on this chart is going to also be a real number. So that's why you can see the two answers here are rational and real. Again, the fact that this is terminating is important because if it goes on forever and ever and doesn't have a pattern to it, that's going to make it irrational. So the fact that it terminates definitely makes it fall over onto that rational side. We don't even have to question it. Square root of 16 over 2, well, that looks a little bit nasty, but as you can see, the square root of 16 is equal to 4. 4 over 2 is equal to 2. So when we figure this whole thing out, what it's equal to is 2. And that's going to make it fit into a lot of categories. Remember, the first category is the natural numbers, which you count. 1, 2, 3, it fits there. It's got to then fit into everything else that's in this illustration. The whole numbers, the integers, the rational numbers, and then the real numbers. Remember, the irrational numbers are separate because if it's in this bubble over here, it's not then going to flow over here into this side of the chart. So it's a natural number, a whole number, an integer, a rational number, and again, regardless of where it fits on the chart, this side or this side, these are all real numbers. So as you can see, as we look at our solutions there, you've got pretty much everything: natural, whole, integer, rational, and real. All right, so as we go ahead and take a look at example 2, in number 2,